Security in software development has undergone a profound transformation over the past 2 decades. Traditionally, security was treated as a final checkpoint. Developers would write code, assemble an application, and only at the very end would a security team review it, looking for vulnerabilities. This approach had a critical flaw. Finding a serious problem at the end of a project is enormously expensive, both in time and in money, because fixing it requires going back through layers of already validated work. The industry recognized this problem and began shifting its practices. 3 major conceptual shifts now define how modern teams think about security throughout the life of a software project: shift left, shift right, and the feedback loop. Understanding these 3 shifts is essential for anyone entering the DevSecOps field. Shift left, bringing security earlier in the process. The term shift left comes from a simple visual metaphor. If you draw the software development lifecycle as a horizontal line from left, conception and design, to right, deployment and production, traditional security was positioned far to the right, near the end. Shifting left means moving security activities toward the beginning of that line, toward design, coding, and early testing phases. The core idea is that the earlier you detect a security flaw, the cheaper and easier it is to fix. Studies in software engineering have consistently shown that a vulnerability found during the design phase can be corrected in a matter of minutes by adjusting a specification document. The same vulnerability found after deployment can require weeks of work, including patching the code, retesting the entire application, redeploying, and potentially notifying affected users. Concretely, shift left translates into several practical actions. Threat modeling during the design phase. Before writing a single line of code, teams analyze what assets they are protecting, who might want to attack them, and what attack vectors exist. For example, when designing a login feature, the team asks, what happens if an attacker tries thousands of passwords automatically? This question, raised early, leads to building rate limiting and account lockout mechanisms from the start. Secure coding standards and training. Developers are taught to write secure code by default. They learn about common pitfalls such as SQL injection, where user input is directly inserted into a database query without being sanitized, or cross-site scripting, where malicious scripts are injected into web pages viewed by other users. By knowing these risks early, developers avoid introducing them in the first place. Static application security testing integrated into the development environment. Automated tools scan the source code for known vulnerability patterns as the developer writes it, or at the very least before the code is committed to a shared repository. You already experienced this in the workshop on setting up a basic pre-commit rule. That was a direct application of shift left. Pre-commit hooks are a textbook shift left mechanism because they intercept problems before they even enter the shared codebase. Code review with a security focus. Peer review processes include security checklists, ensuring that a second pair of eyes evaluates the code not just for functionality but for potential vulnerabilities. Shift left is not about making developers into security experts overnight. It is about integrating security awareness and automated tooling into the workflow that developers already use, so that security becomes a natural part of building software rather than an external audit imposed upon it. Shift right. Observing security in real conditions. If shift left moves security toward the beginning of the development cycle, shift right does the opposite in a complementary way. It pushes security activities into the production environment and post-deployment phase. At first glance, this might seem like a return to old habits, but the philosophy is fundamentally different. Shift right is based on the recognition that no matter how thorough pre-deployment testing is, real-world conditions always introduce factors that were not anticipated. Real users behave in unexpected ways. Infrastructure configurations in production differ subtly from test environments. Attackers find creative combinations of weaknesses that automated scanners never predicted. Therefore, actively monitoring and testing security in production is not a sign of failure. It is a deliberate and mature strategy. Shift right manifests in several important practices. Dynamic application security testing in production-like environments. Rather than only testing static code, dynamic application security testing tools interact with a running application, sending requests and observing responses to detect vulnerabilities like insecure authentication flows, exposed sensitive data, or misconfigured access controls. This type of testing requires the application to actually be running, which is why it belongs on the right side of the lifecycle. In the workshop on mapping the OWASP Top 10 on the pipeline, you already began to see where dynamic application security testing fits compared to static application security testing. Penetration testing on authorized perimeters. A professional or a dedicated internal team deliberately attempts to compromise the application using the same techniques an attacker would use. This is done in a controlled, authorized context, but it targets the real or near-real application. Penetration testing is a quintessential shift-right activity because it simulates the adversarial conditions of the real world. Continuous monitoring and logging, security events are captured in real time in production. Unusual access patterns, repeated failed login attempts, or anomalous data transfers are flagged and investigated. This is not about catching bugs in the code, it is about detecting attacks as they happen. Tools that aggregate logs and raise alerts when suspicious sequences of events occur are a key part of this approach. Chaos engineering and resilience testing. Some teams go further and deliberately introduce failures into production systems to verify that security and reliability mechanisms respond correctly. For example, simulating the shutdown of an authentication service to verify that the rest of the application fails securely rather than bypassing authentication checks. Bug bounty programs. Organizations invite external researchers to find and responsibly report vulnerabilities in exchange for recognition or rewards. This is an extreme form of shift-right, effectively crowdsourcing security testing by allowing ethical hackers to probe real systems. Shift-right does not mean that pre-deployment security is less important. It means that a mature security posture accepts that real conditions will always differ from test conditions, and prepares accordingly. The feedback loop, connecting left and right into a continuous cycle. Shift left and shift right, taken alone, could appear to be two separate and somewhat contradictory impulses. The feedback loop is the concept that unifies them into a coherent and continuous security strategy. The feedback loop refers to the systematic process of taking information discovered on the right side of the lifecycle, in production, through monitoring, through penetration testing, through real incident analysis, and using that information to improve practices and tools on the left side of the lifecycle for future development. Without a feedback loop, shift-right findings remain isolated incidents that get patched reactively without generating lasting improvement. With a feedback loop, every vulnerability discovered in production becomes an input that improves coding standards, updates automated scanning rules, refines threat models, and trains developers. Here is a concrete example to make this tangible. Suppose monitoring in production reveals that attackers are successfully exploiting a server-side request forgery vulnerability in a recently deployed feature. A server-side request forgery attack occurs when an attacker tricks a server into making HTTP requests to internal systems that the attacker should not be able to reach directly. The steps of an effective feedback loop would be: 1. The incident is documented in detail. What code was vulnerable, how the attack was carried out, what data or systems were exposed. 2. The development team patches the vulnerability in the current application. 3. The static application security testing rules are updated to detect this pattern of vulnerability automatically in future code. 4. The threat modeling templates used during design are updated to include server-side request forgery as a specific threat to evaluate whenever a feature involves making outbound HTTP requests. 5. A new item is added to the secure code review checklist. 6. A brief internal training session or documentation update is shared with all developers, explaining what server-side request forgery is, how to avoid it, and what to look for in code reviews. After this loop, the same class of vulnerability is far less likely to appear again because every preventative layer has been strengthened. The organization becomes more secure not just by fixing what broke, but by learning from it. The feedback loop also applies at a smaller scale within a single sprint or development cycle. For example, when a pre-commit hook blocks a secret from being committed to a repository, as you practiced in the workshop on simulating a committed secret and correcting it, the developer who triggered that block receives immediate feedback. If the tooling is well designed, it explains what rule was violated and why it matters. This micro-feedback loop teaches the developer in the moment, gradually building secure habits without requiring formal training sessions. In a broader organizational sense, the feedback loop creates what practitioners call a learning security organization, one where security incidents are not treated as embarrassments to be hidden but as valuable data points that drive continuous improvement. Why these three shifts work together? It is important to understand that shift left, shift right, and the feedback loop are not alternatives, they are complementary and interdependent. An organization that only practices shift left will have solid foundations but will be blind to the unexpected vulnerabilities that emerge under real-world conditions. An organization that only practices shift right will spend enormous resources fighting fires in production without ever addressing root causes in the development process. Without a feedback loop, both the left and the right remain isolated silos that improve very slowly, if at all. Together, these three shifts create a continuous, self-improving security posture that spans the entire life cycle of software. This is precisely the philosophy that DevSecOps embodies. Security is not a phase, not a team, not a final gate. It is a continuous practice woven into every stage of building, deploying, and operating software. For a DevSecOps specialist, mastering these three shifts means being able to identify, at any point in a project, where a given security activity belongs, how it connects to other activities, and how information should flow between stages to make the whole system more resilient over time. The tools you will encounter throughout this course: static application security testing, dynamic application security testing, software composition analysis, container security scanning, penetration testing frameworks, each have a natural home within one or more of these three shifts. Understanding the conceptual framework makes it much easier to know why each tool exists and when to use it. To summarize the three shifts clearly: Shift left means integrating security as early as possible in the development lifecycle, through threat modeling, secure coding practices, pre-commit hooks, and static analysis, so that vulnerabilities are prevented or detected before they reach production. Shift right means actively testing and monitoring security in production and production-like environments, through dynamic testing, penetration testing, continuous monitoring, and log analysis, so that real-world conditions are accounted for and active attacks are detected. The feedback loop means systematically taking findings from production and post-deployment activities and using them to improve design, coding, and testing practices, creating a continuous cycle of learning and improvement that strengthens security across the entire organization over time.